Okay, so let's start with the lesson number 2. So as well, at least those of you who are here, so you notice that we have different lecture time. So let's try to finish kind of early enough. So I need to be at 1 o'clock in Pasila to give a presentation. So that's why we started a bit early this week, and actually next week as well. So we have, well, I sent you email about it, but maybe to mention again, so that next week we will have the lecture on Wednesday, and the lecture hall was also different. It was some B something, but it's in the email. So all of you got the email? Yes. Good, so that you're registered. But yeah, you can check from there the lecture room, and we will post also in Slack information about that. Okay, but maybe we start directly with the lesson, so that we have enough time to go through the materials. So last week what we learned was basically to play around a bit and see how to create geometric objects using this Shapefile module or library. And that is kind of, it might be a bit boring, but it's really good to understand those things, because now we are going to see and use those exactly the same geometric objects, and we will see how they are actually underlying in the framework of Geopandas that we are going to learn today, and that is the package that we are going to use quite a bit during the next 6 weeks. So it will be a familiar package for you. So basically the contents for today is to get a bit of introduction of some basic functionalities of this Geopandas data, such as reading and writing data from shapefiles, for example, and how to create geometries into GeoDataFrame. That is similar to DataFrame that we saw with Pandas, but now we have kind of geometric capabilities extending the capabilities of data frames. And then we will have a lesson about coordinate reference systems. That is, of course, really important topic when doing GIS. So, but let's start with the introduction to Geopandas. These links might not yet work. I tried to fix those, but at least the banner in here should work already. So now if you want to follow, I recommend launching the CSC notebook thing, because the binder instances, well, now this seems to be, yeah, okay. Now this seems to be launching as well, but it might be that it actually misses one package that we are going to use. Might work as well, but I haven't checked that yet. But at least the CSC versions work. So if you launch using this CSC notebook, using this button, and then kind of do the normal procedures using the GIS Jupyter Lab instance that is there. So you should be finding notebooks in here, and then there's the lesson 2, and we will start with the Geopandas basics notebook.
It's not there.
Yeah, I'm only seeing L1.
If you don't see it yet, you probably launched the instance some time ago before the notebooks actually existed yet in the repository that is automatically. So if you don't have them there, destroy that instance and launch a new one. So then they should appear there. So that's the, it took a bit a while so that the CSC system somehow updated and it was visible there. So I was facing exactly the same Same thing, but relaunching the instance helped. So now they should be there because I'm able to see them. Good. But for this week, what we're going to do is that we have a set of package of data. So from now on, typical workflow in the lessons is that we will download some data as a zip file, typically, and then there are some data files, and then we start working on those ones. This is kind of a really typical, first step that in all kind of analysis pipelines that you do, so that you need the data. So we will see, for those of you who are not familiar with Linux or kind of using terminal, so we will kind of repeat these certain things, such as using wget or wget to download some data from somewhere on the web, and then we will also see how to unzip files using Linux terminal. So that's the first thing that we will do. So for this week, so as mentioned, we are going to download some data. So let's see how we can do that using the terminal commands. So how we can first of all launch a terminal in Jupyter Lab is that there's this plus button here. So basically pushing or pressing this button, and below here you have a terminal kind of button, and by executing that one you should be coming into this seeing this terminal window here, and here you have all the Linux commands available for you. So what we need to do first is that we need to basically navigate ourselves into the lesson 2 folder. So we should go to the work. This is now for the CSC version. So let's see if most of you are using this one. So let's do it in Binder. So here you should have the notebooks folder like this. So you go CD notebooks, and here you should have hopefully the lesson 2 like this, and here you should have the IPython notebook files like this. So this is kind of the directory where we want to download the data. So and with the ls, it basically lists all the files inside this directory, if you were wondering what that does. But now what we want to do is that we want to download data from this repository. So we have a dedicated repository for data under here, this AutoGIS organization. So what we can do is that let's just copy and paste this from here, and then take it to the Binder terminal, and with Shift pressed and right click you should be able to do the paste in here. So wget is a command in Linux that you can use to download stuff from anywhere on the internet. I guess at least some of you are familiar, most probably familiar with it. But when executing this one, it takes a couple of seconds, well, maybe even less than a second. Yeah, 0.2 seconds to download this zip file in here. So now if we check what do we have in here, so now we have this l2_data.zip. So now final thing what we need to do is that we need to unzip that file so that we are able to use it. Well, what command we can use is this command called unzip. It's pretty intuitive, and then just specify the zip file that you want to unzip. And just leaving it like this, it will basically unzip the file, and you should have now a folder in here in the navigation panel. And under here, if we go and check the L2 data, so under here you should have two shape files. The first one represents this kind of dam shellfish distributions. So it's a fish species that looks something like this. So it's this kind of fish that you might see in the aquarium. And basically that shapefile that just represents where those fishes can be found globally. And the other one represents the Europe borders as a shapefile. Yes. Now we have the data, and basically we are kind of good to go and start seeing how we can actually use Geopandas to do stuff with this data. So indeed we have two notebooks in here. So we have this Geopandas basics and then this projections notebooks. And the first one that we are going to go through is this Geopandas basics, so that we learn some basic things about using Geopandas. So really the first thing that you most often want to do is that you want to read the data in to Python, so that you can actually start doing some data analysis with it. So we are going to use, as mentioned, Geopandas quite heavily during the course. And the first thing that you, of course, always want to do when you want to start using some packages, that you need to import it. So let's start by importing the Geopandas. And Geopandas is, again, it's quite a long name. So typically you want to give some shorter name for it. And the abbreviation that is typically used for Geopandas is this GPD. So with Pandas it was PD, so Geopandas just adds the G letter in the front. And let's test that this works. It gives some, you don't hopefully need to worry about these errors. We will see soon, but it just gives some warnings about NumPy NumPy D type size changed. But we will see. Hopefully it doesn't cause any troubles. I doubt that it will. But how do we actually read the file from this folder? So it's really similar to what we learned using Pandas. So the first thing really is that we need to specify the file path. So let's create a variable called fp and say that fp equals 2. And here we can use relative paths. So basically, as we know that this IPython or this notebook is located into this folder, and our data is in this folder L2_data. So what we can basically do is that we can just specify that from that L2 data directory, I want to read the data called dam shellfish, and they are all capital letters, and then lower letters, distributions dot shape. So as you can see from here, so this is the terminal window, shapefile always contains quite many different files that are actually associated to the shapefile. So we have the projection file, then we have the geometric objects in this shape SHP file, and then the DBF contains the attribute information. So the one that we always want to read or choose from these files is this .shp. So when we specify the file path, to, for Geopandas, we use that shape extension file or the file format in here. So now we have the file path specified, and then when we want to read the data in, is that we basically call Geopandas. So let's read the data into a variable called data, and let's call GPD. So and dot, and here again we have quite a lot of different functions available for us, but we can use this read file function, and what we are specifying in is this FP variable that we specified here. And now if everything works okay, we should be able to read it in, and yes, no errors or even warnings at this point. And now let's see what we have. So if we press type and put the data variable in, we should be able to see what kind of data type this data variable or the contents of it is now. And what we can see here is that, well, it's a geodata frame. So now we have something similar than Pandas data frames are, but with some new capabilities related to the geometric objects and so on. So let's take a look how the data looks like. So by specifying data.head, we can, as you can see, use exactly the same functionalities that we saw already with Pandas. So data.head will print out the first 5 rows of your geodata frame, and we can see that, well, there is quite plenty of attributes in this geodata frame. The ones that we are going to use during this tutorial is this binomial column in here that basically contains some subspecies of that certain fish that we are now taking a look at. Then we have some information about the year that it was added to this one, and so on. But yeah, we are not maybe that interested in nothing more than this binomial at this point. Of course, when kind of dealing with spatial data, the first things that you most often want to do is that you want to see it. How does it look like? So let's see how we can actually plot this data that we just downloaded and read to the Geopandas. So data.plot is a function that can be used to, okay, we need to use some magic commands in here. So now we saw that it did something, but it didn't show the map. So we need to use this matplotlib, this percentage character, and then matplotlib space inline. And this is this kind of magical command related to the Jupyter notebooks that will basically tell to the notebook that, okay, whatever is done now with this matplotlib, it should be printed out below here. And this is now exactly what we will see. So as we saw, so just passing the geodata frame and specifying .plot, it will produce you a map. And this is, of course, really the first steps that you want to do when having spatial data. So you want to see how does it actually look like, so that you can understand a bit what kind of data we are dealing with here. So as we can see from this map, so well, I have seen this already a few times, so I can recognize a couple of places from here, such as this South American borders from here. So this is basically where the fish that we are now interested in is living. So they are basically on the coasts of South America and the kind of Central America, and then in the Pacific Ocean. And I believe this is something that belongs to Australia and so on. But anyway, you can already kind of get a bit of patterns and see patterns based on the data that we had. So really simple thing and fast to do, to read the data and plot first maps out of it. Did everyone who managed to actually get the notebook working manage to do this? Yes, good. Okay, so now we have seen how to read the data, how to, well, first see a bit what kind of attributes it has, and how to create a plot. So let's now see how we can actually write a shapefile. So of course that is also a really important thing that you need to do, so that you're able to save the things to disk that you have done with Geopandas. So what we will do here is that we will select first 50 rows of the data, and then we will save that as a kind of subset of our full data file that we have. So as we have done this with Pandas, so the first thing you need to do is that you need to specify the output file path. So what is the file name and the path that you want to, where you want to save your data. So let's create a file path for the output file. And here we will create a variable called outfp. And again, here we can use the relative path. So we want to save this data into this L2 data folder. So I just specify L2 underscore data, and then I specify this, and then I say that this should be saved as damselfish distributions underscore selection dot shape. And again, what we want to call it is this shape file name. When doing analysis, well, any kind of analysis, so I really recommend trying to use as specific and intuitive file names as possible. They might not be important when you are just working with them because you remember what this file is about, but there are situations like what I just did during the weekend, is that I have done some work like 2 years ago, and then I needed to reproduce the thing. So, well, because I have named the files in a way that it's fairly intuitive to understand what this file contains, it was quite fast and easy to actually reproduce the thing. But if you have some file names like data1, data1x, data1xxu, and so on, so it's really difficult to understand at all what do you have there. So these are not related to any Python thing, but it's just a generic data management, so that you specify as intuitive file names as possible and as specific, kind of describing what this file contains. Well, this is now just a selection of this file. Of course, we could make it even more extensive, like a selection 50 rows or something, but for this case, now this is enough. Okay, but yeah, so how do we write the shapefile? Well, first of all, we need to do the selection. So let's select the first 50 rows. Does anyone has an idea how we could do this? how would you do that? Select first 50 rows. Of course, you can read the materials, but any thoughts? There is a really handy trick for doing that, but you should know even a couple of ways of selecting some rows from the data. Any thoughts? Yeah. Yes. Good. You can use log. That's one way. Yeah. So basically, what you can do is that you can specify data.log, and then inside here you can, for example, specify from 0 up to 50, and do it like this. And this is good in a way that we could, for example, also say that let's take the rows from 20 to 50 and so on. So this is a good way of doing it. And you can here also specify the columns that you want to use. So this is one way. One really handy, and the other one, actually before going to the one that I want to show you, is that you can basically use in a similar manner as what you do for specifying list indices. So you can just say data, and inside the square brackets you can specify that take everything up to 50, and this is a one way. Then there is a third way that is kind of maybe explains a bit how this dot head actually works. So we can actually use this data.head to get the selection out. So what we have typically done, and how we have used this data.head, is that we have just wanted to print out the first 50 or first 5 rows, for example. But what this data.head actually returns, it returns a data frame based on that, well, now, for example, the first 50 rows. So it's actually kind of doing more than just printing out stuff. It actually returns you some values, and it actually returns the geodata frame based now for the first 50 rows. And if you would say data.tail, you would get the last 50 rows from the data frame. But let's now do it like this. So we do a selection, and let's create a let's just call it selection here. So now we should see that there is about 50 rows available. Yeah, 50 rows and 24 columns in the selection variable that we just printed in here. Okay, but how do we save this selection to the disk? So now we have determined the output file path, and then how do we write to disk this data? Is that we just call the geodata frame that we are interested in to saving. So in this case, this selection, and then press dot, and then we have this to file. So we have basically two functions in Geopandas, read file and to file, and those two functions are what you need for reading and writing data to file. So now the parameter that we want to use here is to specify the output file path, and what this should be doing is that it should save file with that file name. And now when we go here, we should see, let's see if I can get this wider. Yes. So now what happened was that we had these 5 new files in here, and that is the selection that we just saved. So it's fairly simple thing to do. Now if we would have time, we could actually have a short break and exercise reading that file in, but now in terms of time we want to skip that. but you can do that on your own time. And of course, this is something that you will do fairly frequently in the exercises, for example. Good. Does that seem more or less? It should be pretty straightforward thing. Yes, good. So let's now take a bit closer look of what is actually happening and what makes this geodata frame a geodata frame, or kind of geometrically interesting data format and data structure. So in this data, we can first of all, let's print the columns. So data.columns is the function that you can use to print out all the columns that you have in your geodata frame. So we can see that we have plenty of different columns in here, but what actually is interesting here is this column called geometry. So let's take a look. How does that look like? So let's call data. Let's print it. Print data. And inside the square brackets, call the data geometry. And it took a bit. Well, maybe I just take the head so I can get the first 5 ones. So data geometry.head. So what we can see here is that what this returns is this kind of information. And if you remember from last week, this might seem quite familiar to you. So we have this kind of information called polygon and then some coordinates inside in here. So basically what is under the hood, as I have already noted a few times, is that we have these shapely objects inside the geodata frame, and that is actually representing the geometries in Geopandas. And as you might guess, if you have the shapely geometries inside there, and then last week you learned that you have different kind of attributes, different kind of functionalities of those shapely objects. So of course those are also available for you in this Geopandas. So Shapely does quite a bit of things actually under the hood. So that's kind of good thing to understand. And let's take a look a bit of what we can do, for example, with this this file in here. Let's first calculate the area of the first 5 rows in the data frame, and let's make another selection of the data so that we just take the first 5. So let's create a variable called selection and say that selection equals to data. And now let's use this other way of selecting data. We could use the .head, but basically specifying 0, 5. This is a way how we can actually take the first 5 rows from our data frame. And let's print them out to see that we actually have 5 rows. Yes, it seems that we have. And now we have all the same attribute data that we saw previously. So now what we are interested in is exactly this last column here called geometry. So let's see if we start to iterate over the rows and try to see what we have in there. So let's iterate over the rows and calculate the area. So as you might remember how we created a loop and iterate over data frames or geodata frames. So again, we can use exactly the same functions as with pandas. So we specify a for loop starting with 4, and then using this iter rows functionality of pandas, it actually returns you the index value, because in the data frames you always have this index running in here. So the first thing that it will return is the index, and the second one is the values in that row. So let's call for index, comma, row in this selection that we just created. Selection dot, and then we have the function iter rows. And it needs to be having this parenthesis because it's a function. So in here, now we are iterating row by row this stuff. And well, let's first of all calculate the area of the polygon. So now we have these 5 geometries here, and as we have this polygon object inside the data frame, we can calculate the area using the Shapefile functionalities. So get the area of a polygon. So let's create inside this loop. So now we need to use the indentation. So we put either 1 tab or 4 spaces to do the indentation, or to indent the code block. And then we create a variable called poly_area. And here, now what we want to do is that we want to take the geometry of that row that we are iterating over. So we specify row, and then inside these square brackets. So in a similar manner as you are doing, for example, calculations between columns, summing column 1 and column 2, inside these square brackets, specifying the column name that you are interested in, you can get either all values of that column if you're taking the values from a geodata frame. In our case, we are taking the values from a specific row, so we will only get one value, and that is basically the geometry of that row. And when we have the geometry, basically what this represents is a shapely object. And if you remember from the exercises, a shapely object has this attribute called area that tells the area of the polygon. So we can basically pass information row geometry dot area, and we will basically get the area of that polygon. And let's just print out that information. So let's print polygon area at index. Now I will also show you some more tricks doing this. I will explain you in a short time. Is .3f. This is something that we actually saw last week a bit. Index equals the index from here, and the area equals to this poly area. I will explain you a bit, but let's first check that. Now this should print out from those 5 rows that we have in here. It should print out the area and the information about the index that we are running. And this is exactly what we see. So the key thing here is that now we saw that it's possible to basically use the same functionalities that Shapefile has to actually access the area, for example, access the centroid or whatever things that we practiced last week. Then about this print statement here, so a couple of mentions about this. So now we are using, again, last week I explained a bit about this already, but maybe to kind of, well, shortly describe what is happening. So we have in Python this function called format, and this allows you to basically insert some stuff inside the text that you are writing. And with these curly brackets and the name that you specify in here, it's basically possible to kind of use name tags that you then inside this format parentheses. So this index, basically whatever value you pass to this one, it will be inserted in here. And the same thing applies for this one. So this area, so again we have this area in here inside the parentheses, and what is kind of inserted into the string is the information about the polygon area that comes from this variable. What then happens in here is that we also round the values so that we only get 3 decimals for that, and that is what we are basically seeing. What is important to understand that these can be whatever. The names that you tag inside the text, so this is now index, but it could be, for example, my_index, and it would work as well. But now what we should do is that we should also modify these to correspond to the name that you specify here. So these are really useful things, and let's check that it works, and well, it does. So these are good things to know. It's not really the core focus of this course, but these are tricks that you will learn hopefully also during these 7 weeks now. Yes.
Oh, sorry, but the polygon is like every polygon at index 1 is they are a separate polygon each, or are they creating the polygon out of these 5?
Basically, yeah. So let's do so that I create a new. So now we have the selection and we have those 5 rows. So we have a geodata frame, and now we have selected 5 rows. So if I take that selection and plot those things. So now we can see that, okay, this seems to be 5 polygons. This might be the south coast of, or the west coast of South America. So those 5 rows and the polygons that are associated to those rows, so they are basically single polygon at each row. If there would be multi-polygon, we didn't really go through those things, but then the single value on that row might actually consist of multiple polygons. But that's a different kind of geometric data type. But yes, this is what happens. Good. So now, well, we saw that we can access those Shapely objects, well, now in this case now row by row, and then we were able to do the area, and well, we could be able to do whatever things that are available in Shapely. But of course, this is not the most kind of efficient way of doing things, and luckily you don't need to do it if you're interested in calculating areas or centroids. You don't need to iterate over the data frame. You can do it directly, but I just wanted to demonstrate that this is also possible to do. So let's now see that how we can actually calculate the areas for all of those. How many, well, we can check how many rows do we have in the data. So let's calculate the area for all of those 231 polygons that we have in here. And let's store that information into a new column called area. So calculate the area of polygons into a variable, not a variable, into a column called, well, area. So we have this data frame, and how were we able to create new variables or column names into that one, attributes is that we specify inside these square brackets the name of the column that you want to create. And then typically you want to assign or store some values into that column. And in our case, what we want to store in there is that we want to take all the geometries from this data geodata frame and just press dot, and here we have a function or attribute called area. So what this does is that it will basically go through all those polygons and kind of get the area of each one of them and store that information into this column that we will create here called area. That is kind of intuitive name. And let's now print the, well, let's print the tail, so the last 5 rows of our data frame. So now we can see, or should be able to see, that now we have a new attribute called area, and these are the areas that are associated to each row in this data frame. So representing the area of this polygon at index 226 at this case, or in this case, and so on. And now, as we have the area, these are basically numbers that we have, so it's really easy to calculate, for example, the minimum and maximum and average area of those polygons that we have. So let's do some calculations. So let's calculate max, mean, and average size of the polygons. So let's say that max area equals to data, and the column that we created was called area. So we call data in square brackets area dot max, and these are the same things that we have been using with pandas. Then I copy paste a bit and call min area is data square brackets area dot min, and the average or the mean area is data area dot mean. So now we should have all those variables in here, and I can print out them. You don't need to do this, but I just print max area, and then let's create a new line after this one. So there's this backslash n that creates a new line. So let's say backslash area new line. Actually, not yet here, but here we use the same format thing that we did earlier. So let's, in these curly brackets called max, and then a new line, and then mean area colon min, and then a new line, and then mean area and then mean. And then again, after this string definition here, we say dot and format, and then we need to fill in these variables that we have in here. So we say that max equals to max area, min equals to min area, and this mean equals to mean area. And now what happens is that, well, here we have these maximum area seems to be 1493, and those are basically decimal degrees that we have in here. Minimum is something like this, so quite small, as we have this minus 15 in here, so we have a lot of zeros before this number 2 in here, and then the mean or average area of those polygons seems to be 19. decimal degrees. Good. And indeed, kind of this is kind of escape character. Have we went through these escape characters? Do you remember of these things? This is just kind of a character related to when you format strings. So there is a special character that you can use to specify that I have this piece of text, then I want to jump to the next line. So this \n just does that. So now as we can see, we have the max area, and then we inserted the value, and after that we jump to the next, and this is what we actually see in here when we print out this text. So nothing really special, but something useful to know as well. Good. Does these things seem clear? I'm sorry, I might go a bit fast, but hopefully you can follow more or less and understand what is going. This is just a quick intro of the really basic things that what we can do with the geometries. Let's now see another example of one of the basic things that you quite often need to do. So the thing is that you want to create a geodata frame from scratch. So you have some, for example, coordinate information, and you basically know already how to create shapely objects from that coordinate information. But let's see how we can create a geodata frame based on those coordinates, so that you are able to actually save that data, for example, as shapefiles. So this is something that we missed last week when doing the exercise. Yes, you have a.
For example, when I get the shapefile, I get the column geometry because how can I get the
No, so you have a shapefile and then you.
I don't have this column geometry, for example.
Yeah, okay. Basically, if you have a shapefile, and if that's a valid shapefile, it will always have the geometry column there. So that's kind of because shapefile, well, if it's kind of correct format, so it is kind of there, because this geometry column will be created by Geopandas actually. So what it will do is that in the shapefile you have this .shp file, and that is actually, well, that's the S3 standard of how the geometries are represented. So what Geopandas does is that it will actually read that file and read the coordinate information and the kind of geometric information from there and transform that into this column called geometry. So it will always be there. Yeah, that's actually a good question. And the same thing happens. So shapefile is one file format, but you might have GeoJSON, you might have GeoPackage, and different kind of data formats. So what Geopandas always does is that it kind of harmonizes the things, and it will always be in this geometry column. So it's kind of a good thing to know. It was a good question, so thank you for that. Good, but yes, so let's create a geodata frame from scratch. And what we can, of course, use for this is the package Shapely. Let's import the packages. So I just now import Geopandas again. It's not necessary because it's in the memory, but maybe to keep these things closely together, I import it again. So now we are going to use this Shapely geometry. So from Shapely.geometry, import point and import polygon. So this is something that we learned last week. And well, if you haven't done yet the exercises, you will still probably learn some things about them, but this is basically these objects that we are going to use. And let's create first an empty data frame or geodata frame. And what we will then do is that we will populate this empty geodata frame with the geometries that we have. So let's call a variable called new data equals to gbd and dot, and then we have this geodata frame, and then we put parentheses, and this is a way how you can create an empty geodata frame. So in a similar manner as you were able to create Pandas data frame, so exactly the same functionality applies to geodata frames using this syntax here. And let's see what do we have when we print out this. So now what we have done is that we have just initialized an empty geodata frame, and this is what we will see when we print out the new data variable in here. So as we saw from the earlier examples, the geometries, they are always stored in this geometry column. So that is kind of a well, key hint. So probably what we need to do if we want to actually store and create a geodata frame, so we need to create that column called geometry. So let's create a column for the geometries, and now we say that new data equals new data geometry. So this is again how we can create a new column, equals to none. So let's not put anything in there yet, but just to create and initialize this column. And now when we print this thing is that we can see that this yet we have empty geodata frame, but now in these columns we can see that okay, we have this geometry column in here. Great. So the next thing what we want to do is that we want to create a polygon that represents the Helsinki Senate Square in front of the white church. So let's just create a more or less rectangular polygon. And for that we need to have coordinates representing the kind of nodes of the polygon. For that I will just actually go to the lesson materials here and copy and paste this list in here because I don't want to write these things. So there are 4 coordinates, x and y coordinates representing each corner of the Senate Square, and like this I'm able to copy and paste it here, and then let's put a comment, coordinates of Senate Square, and then let's create a polygon. So I will create a variable called poly and say poly equals to polygon in a similar manner as we learned last week. And what we should pass inside here, so as you might remember, what polygon takes as an input is a list of coordinate, x and y coordinate tuples, what we see here. So what is a tuple? It's similar object as a list, but they are immutable, so you cannot actually change these values once they have been initialized. So that's a difference between a list and a tuple. So yes.
Could you explain that a little more? See, we can't change one point at a time, or what does immutable mean?
Yeah. Good. really quickly. So basically, a tuple is basically created by using these parentheses, and it works a bit in a similar manner as a list, but the thing is that now inside this tuple we have two values, so these coordinates in here. But what is the difference between a list and this is that if you, for example, maybe we just do this now like this. So now we have these coordinates, and let's take the coordinate, let's say C1 is the coordinates at index 0. So now we should have one tuple in here, and we can check that what is the type of this one. We can see that, okay, it's a tuple. So the difference between tuple and a list is that, well, first of all, it looks different. So indeed it has the parentheses, but with list you would be able to say that let's change this value to something else, like A. But what this basically gives you, this tuple, is that the tuple object does not support item assignment. So it's immutable in a sense that whatever values you have inside there, you cannot change them afterwards. But if you would have similar C1L, so I will just convert that tuple into a list. So with this list and inside these parentheses, I can do that. So now let's take a look. So it looks exactly similar, but now they are square brackets. And now if we do C1L equals to A, now we don't get an error. And basically if we print out this, so now we were able to actually change the values. These are these kind of immutable, so unchangeable data formats are useful in certain aspects, because you might need to have the kind of restrict the ability to change some things. In this case, it might not make sense, but in some other cases it does. So that's kind of difference between tuples and lists. So they are quite similar data types, but not still quite.
And Polygon takes only tuples.
This would work also with lists.
Would?
Yeah. But basically we could change these into square brackets and it should still work. It doesn't matter, it just wants to have an iterable so that you have two values in each of those kind of lists or tuples. But this is how we can create a polygon now using these coordinates that we have in here, and let's still print out the one. So now we can see that we have polygon with these coordinates. Okay, so the next thing what we want to do is that we want to insert that polygon inside our geodata frame. So to refresh your memory, we have this new data geodata frame that still does not have any values. It just have a none basically there. So what we want to do is that we want to insert this geometric object to row number 0. So at index 0. We insert that and insert the geometry to column geometry at index 0. So index 0 is typically the first index that you want to put it there. Basically there is no restrictions that you could pass it to some other index as well, but of course you typically want to start from 0 when doing these things. So with new data.log at 0 we want to insert the value into column called geometry. And then inside there, what do we want to assign there? So at index 0 in column geometry, the value should be the polygon that we created. So this equals to poly. And now when we print out the new data, we should see that, okay, now we have a geodata frame with column geometry and it has some polygon information in there. So basically at this point, we would more or less already be ready to save the file into a shapefile. But there are kind of few steps that we still typically want to do. First of all, having shapefile without any attribute information is typically, well, not good. You could do it, but typically you want to see something like what does this shape actually represent. And the other thing is that we need to define the coordinate reference system for the shapefile. So let's first add some information that is useful to understand what this polygon is. Yes?
I have a question. If I assign a variable to, or like some data to a certain position in the data frame, why do I have to use block and cannot use the square brackets?
You mean like new data geometry equals to something?
Yeah, I mean the 0 there as well. So like a second square bracket or something. Because like if I would access it board, right? I can say data to the board.
So is this something that you were, or still more?
I would like after or before geometry, I would add another square bracket.
Like here.
Yeah.
And the other one you need.
Close it also before the opens.
Like here.
Yeah, and then that.
And would like this.
Yeah, because I could access values like that, but I cannot change them like this.
Yeah. Basically, let's see. This will work. So it's something that, because the data frames and geodata frames are a bit different than lists. So this is basically, if we would think that this new data is a list and then we would kind of put at index 0 something in there. So this should work. But how Geopandas and Pandas in general works, that like specifying and with the square brackets, things like this, you need to kind of be more specific and say what is the start and stop value of that. So if you specify 0 to 1, this works, but indeed with 0 it doesn't. But if you would put this index locator and then specify at 0 in here, so then again it works. So this might be a bit confusing. There are many ways of accessing and putting data there. But maybe the important key message in here is that geodata frames and data frames work in a bit different manner as lists, as this is probably what you are kind of referring to, or maybe, I'm not sure, but...
That's what we talked about earlier, when we talked about like getting like the first 5 elements or something.
Mm-hmm.
So that maybe also was the first time.
Yeah, but this is really, it relates to the syntax how Pandas and Geopandas frame data frames work. So, but they are. It's good if you know one way of doing that, and that's kind of that will get you going. Then once you kind of see and start using more and more of these things, then you kind of typically find that, okay, in these occasions it's actually more useful to use, for example, this iLock. You might have certain kind of script where you have only one number going on, so then using this iLock instead of lock and other things might be more useful. But but there are at least four different ways of actually accessing data in Pandas and Geopandas, which might feel a bit overwhelming when learning the things. But this lock and this way is quite good because you can. It's fairly flexible in a sense. We will learn that. Well, you have already done some selections also with that, so it's kind of a good starting point. Good. Okay, what was I doing? Yes, I wanted to. So now we have this geometry in there, and now what I want to do is that I want to add some additional information with that geometry, so that it's more understandable for someone who actually opens it in Quantum GIS, for example, or in ArcGIS, so that they will know what it is. So let's add a new column and value to that column. So add a new column and insert value. So we can say that this new data dot lock, and again we want to save it to the same index, so at index 0. But now we want to create a column called location, and we want to insert some value in there, and let's say that it's Senaatin tori. So what this will now do is that it will exactly create a new column and insert that value, and this is what we should see. So now when we print out our geodata frame, so we have the geometry, and then we have this new attribute called location, and we call it Senaatin tori. Well, it's the Senate Square in Finnish, basically, and that is what we will see here. So now we're almost good to actually save this thing into a shapefile, but really the last thing is what we need to do is that we need to specify the coordinate reference system, which will be the next topic of this lesson. But let's now just see quickly how we can do that. We will kind of do a more extensive dive into this topic after the pause. But we have this new data, and then this geodata frame always has this attribute called CRS. And if we print out this new data.crs, we can see that it doesn't have any coordinate reference system information associated to it. So if we would now save this thing into shapefile, we would be able to do that. But whenever someone else who are not familiar with the data and he would take it, he would basically need to guess what is the projection or the coordinate reference system of that data. Of course, in this case, it would be possible to guess that, okay, these look like decimal degree values. So probably it's this WGS 84 projection that is in here. But without specifying this, it's impossible to know, basically, by someone else than you who created the file. So let's see how we can specify this coordinate reference system. We will see during the next, this is now one way of doing it. We will see a few more ways of doing it. So just to demonstrate you the one way. So what we can use to specify this coordinate reference system is that we can use this package called Fiona that is actually under the hood of Geopandas. That is a kind of wrapper around GDAL that is basically kind of the really core libraries of GIS things in Python and in actually many other languages as well. So from Fiona or Fiona, I don't know how to spell that correctly, import from EPSG. So this is a kind of function that can be used to specify coordinate reference systems based on the EPSG codes. How many of you are familiar with EPSG? Does anyone know what is EPSG? Good, you will learn that later. So it's just a specific way of defining with certain number a projection that is used. Are the projections familiar to you? Yes, good. So each projection typically have this kind of code called EPSG code, and this VGS or WGS 84 has this EPSG code number 4326. So specify the CRS for the geodata frame. So this is what we want to do. We want to use this function to specify the new data.crs. So new data.crs equals to, and this is a way how we can do it. It's fairly straightforward. So from EPSG and then the code number, which is 4326. So what this will do, we will soon see. So I will print out now the variable new data.crs. So we saw that it's none in here before we do this, and after we run these commands, we will see that what it does is that it actually creates this kind of Python dictionary having certain information inside there. And this is just a standard way of defining coordinate reference systems in Geopandas. So we see that there's this init key in here, and then we have some certain information written like this, and then there are no definitions, other definitions than that in here. And so we will dive more deeply after the pause into these things. But this is what it did. So now we have the coordinate reference system specified into our geodata frame, and now we can save it. Yes?
What is a dictionary?
Yeah, so so what is a dictionary? This is something that we went through when we renamed columns in Pandas. So this is the same thing. So dictionaries are really flexible and versatile in a way how you can use those. But this is exactly the same thing as when renaming. So in the renaming we used basically old name, new name kind of idea. So in this case we have a similar idea that we have certain key called init, which is something how Geopandas wants to have the projection information, and then the value in that key is this EPSG code written in this way. This is just how Geopandas wants this information. So it's just something to know about. But dictionary is the same kind of data format than what we saw when renaming in Pandas. Good. So let's see. Well, now we already have the new data and we have the CRS code or the CRS information associated with it. So the last thing, we can use the same function to save the file. So first what we need to do is to create the output file path. So create output file path. So let's create alt fp equals to, again we will store it into this L2 data directory. So L2 data, then slash senatin well, let's call it in English Senate Square dot shape. This is the file path, and now we can write the data with new data dot to file. So this was the function that we can use to write data into shapefile, and by default it will save it into shapefile. Now when we run this, now somewhere in here we might need to refresh. So now we have this Senate Square DataFrame shapefile saved in here. We have this PRJ file, and as we can see, it contains now information about the coordinate reference system in here. So everything seems to be in order. Good. There is an example in the website, basically a practical example of working with this shapefile. Basically, this binomial attribute contains information about different subspecies of that fish that we have. And this example basically demonstrates how you can find unique subspecies from this data frame, how to basically select data by individual fish, so grouping the data frame based on this column binomial. This is something that we saw in the pandas lessons during the period 1. I believe in exercise 6 there was something related to this one. And then the idea is that you can use this data. It will have the groups as geodata frames. And this shows an example how you can automate this kind of process where you have, let's say you have 1,000,000 rows, you have certain column that has, for example, the names of, I don't know, Finnish guys in Helsinki. We don't have 1,000,000 guys in Helsinki, but let's imagine that we do have. So this kind of process could be used to, for example, group those into separate geodata frames and save those as separate files. So this is something that you can take a look at home. There is basically a small script below here that will create a folder called results. It will, if that doesn't exist, it will create it. Then it will create an output file name. It will print out some useful information, and it will save those groups of fishes into disk. So this is already something that might be quite useful in certain data processing procedures that you might need to do. But we won't now go through this to save some time. But basically now the important things that you should have learned is how to read data, how to write data, and how to create a geodata frame from scratch and specifying the coordinate reference system. So, but let's have a break now at this point.